Hey guys, Ms. Gosling here. In this video, you're going to learn about circular motion and fields. By the end of the video, you'll be able to synthesize what you know about circular motion and gravity. And you'll notice I left in electricity here. We're not going to be talking about electricity, unfortunately, in this video. Okay, so centripetal forces. As you remember, a centripetal force is any force that keeps something moving on a circular path. One example of a centripetal force that we've talked a lot about is tension. We've also talked about both the normal force and gravity acting as centripetal forces, acting as opposing centripetal forces, or as acting as part of a centripetal force. So the key thing here is that both gravity and electricity can act as centripetal forces. And again, in this video, we're going to focus on gravity, but I do want to talk about both of them really briefly. So a really good example of gravity acting as a centripetal force is given in this picture on the left. So the orbits of the planets around the sun are mostly circular. They are technically elliptical, but for the sake of this class, we'll consider them circular. And they are revolving around the sun because of the gravitational force between the sun and each planet. Similarly, a lot of our planets have moons. The Earth has one. Saturn and Jupiter and Uranus and Neptune all have multiple. Mars has a couple. Anywho, all these planets with moons, those moons are rotating around the planet, again, because of the gravitational force of attraction between those two planets, between those two bodies. Electricity, like gravity, can also act as a centripetal force. And one of the examples of that you are probably the most familiar with is the atom. So the kind of traditional model of the atom has a positively charged nucleus made up of protons and neutrons, surrounded by shells of electrons that are negatively charged rotating around that nucleus. So because the nucleus and the electron have opposite charges, they again experience a force of attraction towards the center of the nucleus, which again acts as a centripetal force. So here we have our electrical force acting as a centripetal force, and in our gravitational orbits, we have our planetary orbits, we have the force of gravity acting as our centripetal force. So let's go ahead and look at one example. Given the following information, determine the rotational speed of the moon around the Earth. So we have the mass of the Earth, the mass of the moon, and the distance from the Earth to the moon. So we are given all this information. We also know the value of big G, 6.67 times 10 to the negative 11th. So I'm going to go ahead and draw a picture. So here's the Earth. Here's the moon, and we have the moon traveling in a circular path around the Earth. And it does this because of that gravitational force of attraction between the Earth and the moon. So that means that our gravitational force is our centripetal force. And in this case, we really do only have one force we need to worry about. I know you've done some centripetal force problems with a whole series of forces. With our gravitational problems, we really are only worrying about the one, unless we're looking at things on Earth or things on surfaces. So with that, let's go ahead and finish this problem. So we know the gravitational force is equal to the centripetal force. So if we expand that equation out, that gives us G times the mass of the Earth times the mass of the moon over the distance between them squared is equal to mv squared over r. And you might be asking, okay, so we've got two m's on the left side, one m on the right. What does the m on the right, is that the mass of the Earth or is that the mass of the moon? Well, we know that the m in our mv squared over r equation, so in our centripetal force equation, is the mass of the body that is rotating, the body moving in circular motion. So in this case, because the moon is the body moving in circular motion, we know that the mass in our centripetal force equation is the mass of the moon. If we're looking at the Earth going around the sun, then the mass of the Earth would be the mass in our centripetal force equation. So moving forward, we have the mass of the moon on both sides. That cancels. That's so nice. We also have one r on the right and r squared on the left, so we can cancel out that squared. And that's going to give us, simplifying, v squared is equal to g times the mass of the Earth over r. Thus, The speed of the moon is given by the square root of g times the mass of the Earth over r, or the square root of 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th, all over r, which is 384,400 kilometers, or 384,400 times 10 to the third meters. And we're going to take the big square root of all of that. And that is going to give us a speed of 1,018 meters per second. So there is the rotational speed of the moon. And there you have it, guys. Here is how we can solve these centripetal force problems, or these centripetal motion problems when we are looking at gravity as our centripetal force. Let's go ahead and look at one other thing. So I want to talk about escape velocity. So it's pretty easy for something to stay on Earth, as you know. It's also not terribly difficult for us to send a satellite into space. I mean, it's expensive, it's not easy, but it's in the grand scheme of things, it doesn't require as much speed as as sending, for example, a rocket to the moon. And that is because it is very easy for objects to get caught in orbital motion around the Earth. And it's a little harder to get objects moving quickly enough to escape the gravitational field of the Earth, so to move out of circular motion and to move into essentially linear motion. So escaping the gravitational field of the Earth and being able to travel to the moon or to Mars. Or we have planets, or we have some spacecraft now that have in fact left our solar system. And so that all begins with reaching escape velocity. So if we have a satellite going around the Earth, so we're gonna take a look at this satellite here. That satellite has both kinetic energy and potential energy. And what we need is for the total energy of that satellite must be 0. And the reason for that, so we need k plus u equals 0. And the reason for that is because when we get infinitely far away from an object, the center of a gravitational field, then we know that our potential is now 0. Essentially what we need is for our kinetic energy, which is positive, to be equal to, at minimum be equal to our negative potential energy. So we need enough kinetic energy to bring us out of that potential well of the Earth. So we need to be at a point where the Earth is no longer pulling the rocket ship in towards us. So to do that, again, we're going to need to set up an equation such that our kinetic energy plus our potential energy due to gravity is 0. So what that gives us is that our kinetic energy, which is 1/2 times the mass of our rocket times v squared, and where v is, of course, the speed of the rocket, minus, because our gravitational potential energy is negative, since it's pulling us towards the center of the Earth, so it's pulling us in that negative direction. So 1/2 mv squared is minus g times the mass of the Earth times the mass of the rocket over the radius of the Earth, so over how far we are from the Earth, must be equal to 0. Now I'm getting this left equation from just my basic kinetic energy equation from our energy unit. Our potential energy equation is a little different form than you're used to. You guys are probably used to mgh. But what I'm getting this from is my gravitational potential times the mass of the object that I'm putting in my gravitational potential, which is, of course, the rocket. So we know that our gravitational potential is gm over r, and we're multiplying that by the mass of the rocket. And adding that all together, we want to get to 0. So the first thing I'm going to do is go ahead and divide by the mass of the rocket. Because when I do so, 0 divided by anything is 0, and the mass of the rocket in my two equations will cancel, which is really nice. And now I simply want to solve for v. So I know that VR, 1/2 times VR squared minus g times the mass of the Earth over the radius of the Earth is equal to 0. So doing some whiteboard math, again, doing my whiteboard math, I can go ahead and add my gm over r to both sides. So 0 plus gme over r is just going to give me gme over r, so these two will be equal to each other. Finally, solving for my escape velocity, what I'll get is that my escape velocity is equal to the square root of 2 times big G times the mass of the Earth divided by the radius of the Earth. And again, this is our escape speed. So that's the minimum speed that a rocket needs to have to escape the Earth's gravitational pull. So to be able to get out of our planet and go to a new planet. So let's go ahead and talk takeaways. First of all, gravity can be a centripetal force. And second, the escape speed for an object leaving a gravitational field is given by v escape. It's equal to 2gm over r, where m is the mass of the object that the rocket is trying to escape, and r is the distance, or is the size of that object. So with that, you guys now know about how to understand gravity as a centripetal force. It is your turn to solve some problems. Best of luck and happy solving.